perception and image understanding, but maybe from a different angle. So I'm going to start by revisiting this observation that the architect Antoni Gaudí once made, that there are no straight lines or sharp corners in nature. And yet, somehow, you and I can look at this coordinate system and not be astounded. And yet, pictures like these were actually cutting-edge tools of thought for driving new mathematical discoveries not that long ago, when René Descartes and his contemporaries realized that you could use rectangular coordinates like this to link up algebraic equations and geometric curves to solve mathematical puzzles that had stumped the world for millennia. And it'd be really hard to overstate the impact of this central insight over the past 400 years. This new tool for thinking converted all kinds of problems like these, where you might want to find the set of values that satisfies two equations, into problems that relied on locating points of intersection between two curves. And this was a huge deal, not only for confronting the major challenges of the day in optics and navigation, but also for setting the stage for the invention of calculus. And without calculus, we wouldn't have the modern world as we know it. So no James Webb telescope, no GPS, no microwaves, no ultrasound, no cell phones. But if staring at equations and lines like these remind you of middle and high school math class, maybe we could all just take a moment to marvel at that. Like, how did we get here, where an idea that was revolutionary in the 1600s has literally become elementary today? I think that the story begins some 30 to 80,000 years ago, when anatomically modern human beings began to mark up their physical environments. So in this iconic example, these cave walls, repurposing objects and surfaces in their surroundings into carriers of meaning. Heck, like, just call it what it is. The first user interfaces, right? Each of these iconic images from the history of science captured some new way of looking at and understanding the world. In the case of Darwin's finches, that variation in beak size and shape might be related in a really important way to a bird's ecological niche. Or in the case of Galileo's drawings of Jupiter's moons, that maybe the solar system was organized in a really different way than was acceptable to believe in his time. Ramon y Cajal's much celebrated drawings of retinal ganglion cells exposing detailed structures of neurons and how they talk to one another, and Feynman diagrams in the 20th century opening our eyes to how subatomic particles interact, even if we will never directly observe them doing so. Now, notice that some of these images are quite detailed, and others are quite a bit more schematic. But what all of these examples share in common is that they leverage visual abstraction in various ways to communicate what we see and know in a format that's useful for understanding some aspect of how the world is, how it works. Now, more than any other species, we humans leverage that growing understanding of the world to go and then create new things. For example, our detailed understanding of physical mechanics allowed us to design and then build high-precision timekeeping devices. And a lot of this technological progress has been driven by our ability to continually reformulate our understanding of the world in terms of those useful abstractions that make it possible to re-engineer the physical world according to our design. So translating biological insights into bioengineering, physical theory into advanced physical instruments, neuroscience into medical technology, and quantum mechanics into modern electronics. So what is it then about the human mind that makes these feats possible? So this is one of the key questions that my lab wrestles with. Like, what explains why the externalized abstractions that people create, why do they take the form that they do? And then this is a diagram that I've been using to help me think about the various entities in play. Okay? This is a way of illustrating the standard operating procedure in my home field, cognitive psychology, where the focus is typically on how individual human beings process information supplied by the external world. Here's how that same picture is enriched by the study of social cognition. This is the case where we consider the behavior of multiple individuals at once and how they interact with each other. Now, there's a long tradition in cognitive science of noticing how when these activities are used to learn about the world and then share that knowledge with others, that these activities share important similarities with formal science, even when they're pursued by non-experts in everyday settings. However, something I realized is that the traditional mode in cognitive science leaves out two key components, ones that I think we need to understand how humanity got here and where we're going. First, an account of cognitive tools or technologies, material objects that encode information intended to have an impact on our minds, how and what we think. And second, science's complement, engineering, how people leverage their understanding of the world, whether that's through direct experience or is socially mediated, to then go and create new and useful things. Because without a serious consideration of the engineering half of this picture, we will never be able to explain how and why the world as we know it came to be. So we work in my lab to try to close this loop, to develop formal cognitive theories that explain how we discover useful abstractions, that explain how the world works, this is the science half of the picture, jointly with theories that explain how we then apply those abstractions to remake the world, the engineering side. And the hypothesis that we're working with is that even the fanciest of the cognitive technologies that we've come up with along the way, whether we're using a stone tablet or a cave wall or modern computing systems or generative machine learning-based systems, are at the end of the day grounded in the need to coordinate visual and motor behaviors in the service of concrete behavioral goals. For example, communication and collaboration with other people, present or absent, okay? And thus our challenge is to develop a theory of how this alignment can be achieved between the contents of perceptual experience, the actions that we can perform, and expectations about what others will understand. And I'd like to propose that this alignment relies upon what I've been calling bridging abstractions, so called because they're the core representations that lie at the crossroads between perception, sensory processing, and action, motor execution. In the context of trying to account for how people produce meaningful images and text and other media, the form these bridging abstractions take is assumed to be constrained primarily by a social goal, a communication goal, to make sense. So here are some of the top-level guiding questions that I aim to address in this talk. First, what are bridging abstractions and why are they important? What characterizes the abstractions that people create? And why do these abstractions take the form they do? And my plan is to offer a really high-level overview of two ongoing lines of work, digging into the kind of multimodal generative behaviors that we've been studying to learn about these bridging abstractions. So first, the use of visual abstraction to create meaningful drawings and other kinds of images. And then second, the use of linguistic abstraction to then convey information about the structure of the external world. What makes visual abstraction such a useful domain for our purposes is that it naturally relies on three behaviors that build successively on one another. So first, visual perception, of course. The problem of how we transform raw visual inputs into semantically meaningful experiences. That in turn makes it possible to contemplate visual production or generation, the ability to produce a set of markings that leave a meaningful, visible trace in the physical environment. And those come together during visual communication. How we decide just how to arrange those marks and in what sequence in order to have an impact on other people's minds, to inform, teach, persuade, collaborate, or any variety of other communicative goals that we might have. So to get off the ground with the perceptual question, we started by considering maybe the most concrete and familiar use for drawings and pictures. Creating a drawing that looks like an object in the world. What makes it so easy to tell that the drawing here is meant to correspond to the realistic bird rendering next to it? There have basically been two dominant ways of thinking about this problem of pictorial meaning. The first is that we see drawings as meaningful because drawings simply resemble objects in the world. Like this drawing literally looks like the bird, whatever that means. The second is that drawings denote objects as a matter of convention, and we only learn which drawings go with which objects from other people. So take this Chinese character, for example. In an earlier line of work, my collaborators, Dan Yeamans and Nick Turk-Brown, and I discovered that fairly general purpose vision algorithms, so in this case, neural networks that compose multiple layers of learnable spatial convolutions, were remarkably capable of providing compelling basis for explaining how and why we perceive even quite sparse line drawings as looking like real things. But I quickly realized that you could only go so far with that account. A static, deterministic account of visual processing falls short of explaining how we generate and make sense of drawings like these that you might make in a casual conversation with a collaborator at a whiteboard. What these blobs and boxes mean depends on what you're talking about. So my next goal is to figure out how you might incorporate that information about context and goals to begin to account for the sheer variety of graphical representations that we in fact use to communicate, ranging from more faithful pictures like those on the left-hand side of the slide to the more obviously symbolic tokens on the right-hand side. And our first study tackling this issue asked how people knew when they needed to produce a faithful drawing and when they could get away with something more abstract. In this study, we paired two people up at a time to play a drawing game. The sketcher saw a display that looked something like this, okay? So their goal was to draw the highlighted target object, and then we manipulated what the other objects were around it. On close trials, the distractors all belonged to the same basic level category, so in this case, they were all birds, while on far trials, the distractors were all from different categories. Using this really simple manipulation, we discovered just how flexible ordinary people can be in the way they use pictures to communicate. They made more detailed and faithful drawings on close trials when they needed their drawing to uniquely identify a specific object, instance, and then sparser ones on the far trials where they could get away with category-level abstractions. So here are some examples of the raw data we collected in that study. And then to try to explain what was going on, my collaborators, Robert Hawkins, Mike Wu, Noah Goodman, and I proposed a computational model of the sketcher that used, at its base, a confinet to encode visual inputs into a generically abstract feature space. And then that was nested within a probabilistic model that inferred what kind of drawing then to make depending on the context. Basically, a drawing that was detailed enough to help another agent, the viewer, know which object was the target, but then no more detail than necessary. While we were doing this work, the notion of bridging abstractions hadn't yet occurred to me, but you can think of this model implicitly having learned one in the course of needing to transform purely image-based representations into a quasi-symbolic format that could drive decisions about what kind of drawing to generate on that round. Okay, so I wish I had time to expand on the full details of our modeling experiments, but the take home was that both the capacity for visual abstraction, which we operationalized as network layer in our visual encoder, and a sensitivity to context were critical for capturing how people manage to communicate about these objects at the appropriate level of abstraction, moment to moment. In a more recent paper, we've pushed this idea even further to understand not only the impact of the current context on how people communicate, but also the conditions under which new graphical conventions emerge when memory for previous interactions with the same audience in the same community lead people to produce even more abstract proto-symbolic tokens over time whose meaning depends even more strongly on that contextually shared knowledge. Okay, and so far, we've considered drawings and illustrations that convey information about object identity. But people obviously possess much richer knowledge about the external world than just what things are called or what they look like. And an especially important way that we use visual abstraction, especially in science and engineering, is to transmit mechanistic knowledge about how things work. So what is going on in people's minds when they make this move? Going beyond what's visually salient, let's say about a specific bird and what it looks like, to highlight the underlying physical mechanisms about, say, how birds achieve flight in general. In work led by Holly Huey, a PhD student in my lab, in collaboration with Karen Walker and Charles Liu, we found that when people produce visual explanations for a machine that they just learned about, rather than ordinary depictions, that they reach for qualitatively new graphical elements, including arrows to convey motion and causal interactions, even at the expense of visual fidelity to the target. What that suggests is that however it is people are encoding information from direct experience mediated by the senses, it's clearly a flexible enough mental representation to support really different readouts in the service of different communicative goals. And altogether, what this line of work shows is that it really doesn't seem to be a single set of bridging abstractions needed to explain visual communication, but the contents of this teal box can shift profoundly depending on a person's goals in the situation that they're in. Now, that raises a new question, like what are those bridging abstractions in a given context that support that kind of flexibility? The modeling approach that I mentioned a moment ago in the 2019 study to capture contextual flexibility was limited in a bunch of really important ways. It was reliant on quite heavy supervision. It was unable to capture internal structure within drawings and displayed extremely weak out-of-sample generalization. And the central problem, I think, is that we were ignoring this rich analogical structure that objects and sketches share, in which the relations between the parts of an object, for example, the spatial relations between the beak, body, wings, and feet of a bird, correspond to the relations between the parts of a sketch of that bird. In other words, that the units of action that people perform when producing a sketch, like each stroke they render out, are closely coupled to units of meaning that they are intending to get across, like the parts of the object they think are relevant to include. So in ongoing work, we've been working to more fully expose what those bridging abstractions are in these settings, which we think will mean developing, self-supervised approaches to learning, internal representations that carve up objects into parts that people find natural, that might then endow it with the right kind of inductive biases to generalize to new data and tasks. Okay, now, these same goals have also spurred us to begin exploring our other major cognitive tool, language. So in the last part of my talk, I'm going to highlight just one or two studies to give you a sense of our approach, okay? The phenomenon we're after is how people use language to talk about what they see and want to do. For example, which objects are present in a scene, what parts they consist of, and how to arrange those parts to then create a new object. A remarkable feature of human language is, of course, that it consists of individually meaningful tokens that can be combined in lots of different ways to achieve those goals. Someone might look at these 3 best-selling nightstands from the IKEA catalog and talk about the small rectangular dresser with 2 drawers each with 2 little circular knobs. But there's nothing in principle stopping that same person from reaching for entirely different words to talk about the same object, right? Or invoking its unique product identifier. I looked this up. It's like, for real, the actual ID. You can purchase this object. So given that any given thing can be described in a huge number of different ways, what determines why people favor descriptions at one level of abstraction or another? So in this work, led by Leo Wang, Will McCarthy, and Gabe Grand, we proposed that it might be useful to think of people as inferring from visual inputs a kind of mental graphics program containing commands that correspond to the specific visual elements in their construal of an object. For example, perhaps in this program, a dresser function is invoked that takes a few arguments, such as how many drawers it has, the types of knobs, and so on, the attributes that characterize this dresser. And an appealing property of such a mental graphics program is that it becomes natural to read out linguistic descriptions that reflect that structure. Like, you can think about a 2-drawer dresser becoming like a natural way of describing this piece of furniture. But there is, of course, an infinite number of different graphics programs that could, in principle, render to the same image. And so there's really a huge hypothesis space of possible forms that this bridging abstraction might take, ranging from representations that invoke low-level primitives, like lines and rectangles, planks of certain dimensions, to representations that invoke object-level chunks. So we formalized this variation in abstraction in terms of a concept library that contains the elements that are mentally accessible to a person, and then hypothesized that this concept library would be constrained to be representationally efficient. Okay, so to show you what I mean, consider a simplified 2D rendering of the same dresser. Here are 3 different part libraries that could be used to represent it, from the most compact on the left with just 2 functions, one to draw lines and the other to rotate those lines, to the most comprehensive library on the right with those same base functions as well as more complex ones, like ones that can draw an entire dresser with knobs and even a function that can be used to draw this specific object in one fell swoop. Then programs that you write with those libraries will also be different. With the leftmost library, the programs are necessarily going to be long since you only have lines available to you. With the rightmost library, you can get away with like a minimum length program that invokes just the IKEA _Hemnes _dresser function, right? And for the library of moderate complexity in the middle, you're looking at programs written at an intermediate level of abstraction. For example, invoking a dresser function parameterized with arguments to tell you about its distinctive properties. And we hypothesized that the composition of the concept library that best captured how people carve up these objects depends on striking a balance between the overall size of the concept library, how many concepts they have to hold in mind, and the length of the programs needed to represent the structural motifs appearing across the various objects they could encounter. So then to test that idea, we procedurally generated 2,000 different objects. 1,000 of these were CAD drawing-like from 4 different categories. 1,000 of them were these block towers. So these are just some examples to give you a sense of the kind of variation within and across categories within each object domain. And then we asked people to write descriptions of several objects from each category that were detailed enough so that somebody else reading just that description could recreate that CAD drawing or that block tower. And what I'm showing on the right-hand side of this slide is first the representational efficiency of different concept libraries, from the most compact to the most comprehensive, okay? What we generally found was that libraries of intermediate complexity encoded objects most efficiently by balancing library size and program length, okay? Now, as it turns out, not only were those libraries representationally efficient, we found this striking correspondence between the libraries that optimize representational efficiency with those that scored highly on their ability to predict actual human language, which we measured by fitting a machine translation model to align tokens within these graphics programs to tokens of natural language generated by our human participants. Note that this correspondence was not at all guaranteed, but what it suggests is that people generally prefer decomposing objects into nameable parts that can be reused for many objects belonging to the same class. And then a key prediction of this hypothesis is that what kind of encoding is representationally efficient then depends not only on the structure of any single object in isolation, but what attributes it shares in common with the other objects and entities that a person expects to encounter in that context. So in ongoing work, we're exploring how the concept libraries that are active in people's minds and thus manifest in their language varies between different contexts with different data distributions. For example, in a world populated only with dressers, you might get pretty far thinking just in terms of drawers and knobs. But if you're trying to generate useful descriptions for more of IKEA's diverse offerings, then you might justify activating a larger library of similar concepts to capture all of the physical variation that you're going to encounter. Now, even if the object distribution stays the same, the library that we use to communicate might evolve over time as we establish common ground with other people. So what learning mechanisms might account for that kind of adaptation? So in a recent study led by Will McCarthy and Robert Hawkins with key contributions from Haoyang Wang and Cameron Holdaway, we tried to get at this question by pairing people up now to play a building game. One played the role of the architect and the other the builder. So the architect could see the plans for the towers that they were both trying to build, but couldn't actually place blocks. The builder couldn't see the target scene, but was able to place blocks. So it was up to the architect to provide useful step-by-step assembly instructions, which they typed into a chat window, which the builder could then use to reconstruct the target scene. In this study, every target scene happened to be structured hierarchically. They each contained 2 towers, which each consisted of 4 blocks. And then to see how language behavior changed as participants learned to collaborate better, we repeated each of these scenes multiple times. And what we found was that between the first and final collaborative building attempt, the language architects used shifted to a higher level of abstraction, with references to individual blocks becoming less frequent, but references to entire towers becoming more frequent. And we modeled this learning behavior by combining 2 conceptually simple mechanisms. First, a mechanism for incrementally discovering recurring subroutines in the graphics programs generating each scene. And then the purpose of that mechanism is to augment the library over time appropriately with new part concepts as it saw more data. And then the second mechanism was one for mapping those new part concepts to words to refer to them. And we found that this combination of mechanisms yielded an architect agent that could display the key qualitative behavioral patterns that we observed in our study, including the bias towards tower-level abstractions over time. Okay, so to finish up now, today I shared some pointers to work exploring how people use visual and linguistic abstraction in a flexible manner to communicate about the external world. The larger goal of digging into these multimodal generative behaviors is to understand how our behavioral goals, including communication, constrain the alignment between the contents of our perceptual experience and the content conveyed by our actions giving rise to a set of what I've been calling bridging abstractions that serve to link perception to action in any given setting. And returning to the question I posed at the outset, bridging abstractions are composable representations that are important because they support flexible multimodal behavior. They're useful not because they're static, but because they can be modulated in systematic ways according to an agent's goals and can emerge even over brief timescales. And third, evidence from our modeling studies suggests that these abstractions take the form they do because they provide useful ways of reformatting our experiences and plans in a way that's efficient for thinking and communication. So zooming out a bit more, what's the end goal here? So my mission is to develop cognitive theories of what kinds of abstraction layers humans find useful and build atop one another over time. Because I think they will explain why our current cognitive toolkit takes the form that it does and what future technologies might work even better. And I think that there are major opportunities to imagine tighter links between the kind of innovation that you all engage in here, pushing the frontier of how technologies can be used to augment the way we think, how we collaborate with other people. And I think that tightening those links matters. Because when I think of the difference maker, when I think of what the difference maker really is for human intelligence, it's technology. We're not that anatomically distinct from our ancestors from 30,000 years ago. What's new are all of the ideas and tools that we've invented along the way, including writing systems, mathematical notation, modern data visualization, just to name a few examples. Understanding how these technologies work and how to make them better matters because these tools are the heart of two of the most societally impactful and generative activities that we humans engage in today. Education, okay, the institution, and the expectation that each generation of human learners should be able to stand on the shoulders of the last and see further. And design, the suite of activities and habits of mind that enable people to continually reimagine a different world and then go and build it. So thank you all for listening. I'd like to acknowledge Thank you. I'd like to acknowledge all of the amazing collaborators who contributed to the work in this talk, our funding sources, and I'm happy to take any questions you have. I hope we have plenty of time.
Wonderful. So if you want to ask a question, please just come up to the microphones. But while people are coming up, I just wanted to start us off. And I'm wondering, as you're thinking about these approaches to modeling how, people are able to communicate with different agents, this is obviously something that us as human-computer interaction researchers really care a lot about, right? Like, how can we create an agent, a user interface, or a, large, some type of chat bot or some other thing to do that? And I'm wondering, if we look at your approach to, thinking about how we might be able to model or learn how people are interacting, it seems like these approaches of having very rational actor models are very promising in some ways, but if we look to other areas of psychology, we see sort of these challenges around rationality, and we look at things like boundedly rational, or we look at things like, more of ecological perspective, which I think your work is sort of taking on as well. But I'm wondering, this sort of, to me, strikes this balance between, having these composable parts and rationality that gets you much more generalizability versus sort of, the ecological niches that form and the language that develops and the tools that develop around that and spring out of it. And so I'm wondering if you can kind of muse on that string of words that I just said. Yeah.
No, thanks. No, it's a great and deep question, actually. So there is this tension that is quite live in our field and others, between rational theories of thinking and other approaches, which involve pointing out the kinds of heuristics and or biases that agents rely upon in order to get some job done, right, in time, just in time with the hardware they have, not the one they wish they had, right? And so I think that has been, that divide and that tension, I think, has been deeply distracting to our community for a long time. And there have been some ways through and ways around and ways out that I find really promising. So it's gone by various terms, some of which you used in your question, including bounded rationality. The modern instantiation of that is resource rationality. What that means is that, to some degree, it's reasonable to think of the human mind as having been sculpted by evolutionary forces in order to solve certain computational problems, right? There's a kind of problem to be solved, and then is a useful way of modeling the emergence of certain kinds of mental processes as solving that problem under constraints, the kind of physical constraints of needing to actually wire neurons together and produce behaviors in time in a metabolically efficient way, okay? And so subject to those resources, if you can identify what those resource limitations are and what the objective is, and it explains the patterns of behavior that we observe in people, not only when they succeed and are seemingly obviously rational, but also when they produce other kinds of behaviors too, right, where it may be less determinate, then I really think you're able to make progress towards understanding, psychological mechanisms and those kinds of mechanisms in the mind. Now, I really think that's really promising is like moving beyond like maybe a simplistic way of thinking about behavior in terms of performance on achieving high performance on tasks, but really the goal of cognitive modeling being to explain the actual behavior that people generate. And I think that's why I find the current wave of interest in generative behaviors in people and machines so exciting. Because in many cases, what people say and do in a situation in these really open-ended contexts that we actually find ourselves in every day, it's not always clear that there's like a single right response, right? And so if you can reverse engineer, build a cognitive model that actually explains what people say and do, then you're really onto something, right? So thank you for that question.
Great. So maybe we can alternate, and we'll start over here, and then we'll go here. Yeah.
Thank you. Really awesome talk. I love language. I really enjoyed your presentation. I think your work has some very practical applications, maybe, for example, helping scientists walk the line between writing a bunch of jargon and being understood by other people. So I was wondering if you thought about any specific issues that your work might help solve.
Yeah. May I ask you to repeat? So the part of your question where you're describing how scientists sometimes need to balance the need to
Yes, so for example, I'm not from this community, and one term that I heard in almost every talk was form factor, and to me that just means shape, and so if everyone said shape, I would be happy. But for this community, this jargon has a meaning, and so in your work, you explored, the difference between one word that means that has a lot of information in it, and words that are more, maybe have less information, but are more understandable or more reusable.
Yeah. Okay, I think I'm following, but you give me some body language signals.
Sorry.
If I'm not. No, this is helpful. So, right. So, where are potential sites of application, right? So, I think the idea here is that there's an opportunity to naturalize our computing systems and the environments that we're using to think with in ways that make it easier to onboard new learners, right? New users and learners. Right? So imagine interfaces that fit more nicely with the kinds of abstractions that people find natural, that carve up the world using the concepts that they find natural. And of course, then you can go from there. Because humans are incredibly adaptable, right? In the way that it's part of, this is on display in language, right? Language is a moving target. You can't freeze it in time no matter how hard you try. The reason why language is not static is the world keeps changing because we keep changing it, right? And so acknowledging like our enormous, boundless capacity for adaptation, but also being able to structure the way that we train, let's say, new users or people to inhabit these learning environments and to use these tools, I think could be really beneficial, right? At the early end, let's say in the way that we teach mathematics and like other kinds of, really important kind of foundational skills. And when thinking about upskilling a technology workforce, right? There are so many people who, when equipped and augmented with the kinds of technologies that you all have seen and generated and shared at this conference, right, could be enormously beneficial and impactful for all of us. But it can also be really challenging to learn how to use these systems. And so a good starting point might be to find ways of recovering what those concepts and abstractions are that are natural to people, and then going from there. I hope that speaks to your question.
Hi. Hi, I'm Alex Ola from Google, where I lead the augmented language team. Fantastic talk. I really appreciated like the whole grounding in 32,000 years ago. So wanted to ask a little bit of some other factors around language, both human language and sort of machine language. Obviously, it's extremely hot topic right now with large language models. And I'm kind of curious. As we know, different languages with grammar, structure, vocabularies, etc., writing and notation styles influence representation and thought. And also now with the emergence of large language models and sort of how that influences how we express and interpret meaning. I was kind of wondering, like, could you project how that will influence or change this line of work? Maybe not all the way 32,000 years ahead, but maybe a few decades into the future.
Yeah, honestly, I'd love to hear all of your thoughts about that too, because we're just living it, right? We're like living through history, like another inflection point, it seems. Something that I think is really exciting is that the kind of models that we can build and use are closing the gap with maybe the most complex thinking machine that evolution discovered, like our brains, in other words. And as that gap closes in some ways, right, like I think that that's clearly a very dynamic and contested comparison to make. I think that we can both imagine a world where the ways that artificial systems that can think and plan and act can be used in beneficial ways to augment human thinking and action. And I think that I remain committed to thinking about how we can steward that future, right? And I remain an optimist about the use of technologies as we have continually, and it's part of the reason why I reach for these examples from history, is that each time we've invented a brand new kind of information technology, it's shaken the foundation of our culture, right? And has really opened up new possibilities, seemingly closed others. And we have to navigate those transitions very carefully and responsibly. But I think that we can. We have done it before, right? I actually believe that the human capacity for creativity and thought is boundless when enhanced with tools, including the current generation and the next generation of these large machine learning-based systems. And I think that there remain a lot of challenges, right, as we try to engineer systems that behave in more human-like ways, insofar as that's a path towards safe and reliable and trustworthy AI systems. But I really believe in our ability to figure that out because we've done it before. So that's not that concrete. It's mostly like a kind of optimism that I don't hear that much these days, in some sense, around the development of these kinds of tools. And what I'm hoping is that we can connect, the currently most exciting type of machine learning-based system that mostly employ a text interface, and think about how to connect those and ground those in a way to develop embodied intelligent systems that can think and act and inhabit a human world and coexist with humans safely. So that remains an outstanding challenge that we have not figured out. And I think that that's part of what's really useful about thinking about, how we push around symbols and systems pushing around symbols and grounding them back in the physical world. That seems incredibly important. It's very hard. It's something that evolution has found a solution for in us and other animals like us. But I don't think we've yet engineered, but I think the potential there is really exciting.
Thank you very much. Would love to chat more. Thank
Yeah,
you.
I'd love to.
Right. Longpan Zhen from National Taiwan University. I really like your work. And I really like the concept of the human being has the ability to actually abstractional thinking, especially actually make things actually convey abstractional thinking. And I think in the current era, we actually build a really powerful thing. AI actually can do more abstractional thinking as we do probably in the future. And in the meantime, as our community do, is we build a lot of prototypes actually embody these kinds of abstractional thinking from computer system to the real world. You can see that this maybe in the future will soon become like a loop, that these physical instruments or contraptions actually embodied the abstractional thinking of the computer system, right? And I'm actually started wondering what actually that will happen in the end if all the abstractional thinking actually embodied in all surrounding us, and what we actually will be thinking in that stage. And in that stage, if we are will be creative in that sense, because everything can be so abstractional and everything can convey immediately to the others. And what will be the creative things in that stage?
You can't ask me that. It's like another unfair question about the deep future. Yeah, because you're talking about what are the possibilities. I think there's so many that we can't yet imagine. I won't pretend, right? But something that I believe in is that we're not constrained by the kinds of ways that we use our technologies to think today, right? That we can continually bootstrap ourselves. Okay, let me use this example in case, so not that long ago, the expectation was that most humans would never learn to read. That was just the way things were. And if you ask anyone who was literate, they might tell you most humans didn't need to know how. In fact, it would be impossible to imagine a world where most humans could or did or had to, because it seemed like something that only a few individuals really use, who are responsible for record keeping and copying manuscripts and that kind of thing, and knowledge work. Very quickly, that changed. We now live in a world where virtually everyone learns to read, and is expected to learn to read. If we fall short of 100% literacy, we ask ourselves what went wrong, right? And what we can do with groups of humans who together can think those abstract thoughts, because they can communicate with other people over vast gaps in space and time, was unfathomable to the pre-literate globe, right? I think that it'll be something like that is a place where we could get to if we're able to retool our education systems to adapt to 21st century needs instead of the 20th century ones. So I really think that, against the there are other proposals out there, right? Which is once we have technologies, AI systems that do all the things that we need to do right now, that'll be it. We can just sit back and relax, because that's it. But we're not like that. We're animals or defined by work and activity. What it means to be alive is to be like metabolizing things and be doing stuff. We will find ways to continue to be creative with any set of tools that we invent. And so, we'll see.
Yeah,
But,
thanks.
yeah.
Hi, I'm Hiroshi Ishii from MIT Media. Thank you very much. Talk is so inspiring, but your passion is quite amazing. And I love sketching. Also, you talk about the gears. When I saw the Leonardo da Vinci's paintings, sketchings, I can easily do qualitative reasoning, how machine works. But that's very easy. I think system dynamics is one of the very to understand catastrophic causality chain. System dynamics is a method of simulation. Sketch, text, graph is all kind of outcomes, but how computational model increase of population may make a catastrophic impact to pollution to the environment, also scarcity of air, scarcity of the foods. But those reasoning is very difficult for human beings. In companies, Da Vinci's mechanical sketches. So how your cognitive tools may incorporate J. Forester's like a system dynamics, like a complex computational model. Through these eyeglasses, people can see the world much more differently, more dynamically. So I'm very much interested about the evolution of your cognitive tools repertoire to more hardcore computational stuff, especially for environmental sustainable research.
Wow, okay. What a question. I hope I can say something useful to that. Again, all of you are just asking these like amazing, thought-provoking questions. So, when it comes to modeling complex systems, complex dynamical systems, right, what we have, right, are these sophisticated ways of externalizing our world. Like, we come shipped with a kind of internal world model, right? It's good enough to get by in the physical world, generally without bumping into things we don't mean to, and being able to pick up objects and like pack boxes. Like, there are amazing things that we can do that today's robots cannot, right? And then when it comes to either phenomena that are very small, very large, or very complicated, we built computers to help us with those things. Now, when it comes to running those simulations forward, we make use of what our existing generation of hardware is well equipped to do, and software. And at the same time, we then want to distill out what the summary statistics or what the insights or abstractions are from that. And that's where I can imagine there being more progress to be made, right? It's a way in which we render out what the relevant abstractions are over those simulations from like models of a complex world into a way that's actionable. And a lot of that depends on being able to like formalize what the epistemic goals are that a user or scientist might have in a way that can interface really naturally with the simulation, right? Because we build models of the world not to be point-for-point replica, simulacra of the world, but as abstractions. And in order to make decisions, to guide policy, or just, all of these decisions we have to make depend on what our goals are. So I think a much more like goal-oriented view of how users interact with these systems, and a way of trying to externalize and formalize human epistemic goals, I think is a fertile place to go next here, perhaps.
Great. I really believe those cognitive tools should allow us to ask what if questions. All the possibilities.
Counterfactuals,
We have
and
exhaust all the
hypotheticals.
possibilities. Yeah, but thank you very much.
Thank you.
Yeah.
Andrew Kuznets of Carnegie Mellon University. Fantastic talk, loved it. Anything to do with sense making or anything in that direction is obviously a big fan here. But one question I had kind of for you is, we are interactions builders. We build a lot of systems and we define language of things, right? Whether it's VR or whatnot. I'm probably too late as a PhD student. Like, I won't know the PhD student that invented the word for water, right? Or like frogs, right? But there are people in this room that are creating concepts in their own space, right? Like, oh, here's a concept in VR. Here's a concept in, whatever people are building. So, being in the unique position where you can kind of create the language for certain modalities or just certain experiences, I guess what advice do you have, like having studied how people have done this over so long?
Oh, yeah. I guess working together, right? So it turns out in science and in engineering, you don't have to need to know everything or how to do everything. But what you can do is like decide to work with the groups of people who know how to do the things that you don't, who also find value in the things that you do that they can't, and then find common purpose. So in this case, it sounds like people working in different domains end up having different vocabularies, end up being really useful, and then it can be challenging to, find ways of connecting or communicating effectively, right? Now, if it's the case that, okay, I'm wondering whether you're asking at the level of like a researcher, when, say, striking up a collaboration with researchers like in another domain, it's like if you wanted to like ask the question, like how do ordinary users, for example, like pick up a new lexicon, like a new vocabulary, like a new language to operate in some new domain, right? One thing that could be really great, which I think you all do already, but something that I think there could be a lot more of, we can benefit a lot more of, is the kind of empirical evaluation studies of those systems with those target populations that they might serve, right? And that would be one way of, so for example, in cognitive science, you can construe what we do as user studies in some ways, right? That's our bread and butter. Now, we don't build systems the way that you all do, but we would love to understand the affordances of those systems and how they interact with how people think and act. So there's just all this really amazing work that can be done at the intersection of our communities in any given domain, right? I hope that's helpful. I have some uncertainty as to whether I actually grok your question.
I meant more as we have an opportunity, or we often do, we define the vocabulary for downstream people. So we're, in some sense, we are creating, not the English language, but we are creating a language that then people down the line adapt or use.
Yeah.
And I guess the perspective of, since we have that unique opportunity to define it before people use it.
Yeah. Yeah. You do the baseline study with users who are trying to perform, trying to achieve the goal that you think is the goal they have. Understand what goals they actually have, right? And then understand what vocabulary they already come equipped with, such that your system then interfaces naturally with that one, and then you can adapt it from there, of course, because humans are highly adaptable. Yeah, thanks.
Thank you.
Thanks so much.
Great. So unfortunately, this conversation is so interesting. We could go on for a lot longer, but unfortunately, we have to sort of cut it short for time for other things. So I think we'll take the last question now. So sorry for others. Yeah.
All right, thank you. Soel Kianzot from UBC. I'm going to make a quick question. So we consider the change of level of abstraction in language for communication, and I was wondering, basically the way that we shape the object of knowledge has to do with the level of abstractions, and maybe the way that we change it is the way that we actually know that thing. So it's basically reflecting our own learning. So we are improving when we go to a higher level of abstraction. It's our own way that we know the object versus the way that we communicate it. So can you reflect on the level of abstractions and how we basically improve our knowledge?
Oh,
Thank you.
okay. Thanks for that question, and I will also try to be brief because I know there's more in the program. There's a distinction between the kinds of abstractions we discover when we're working on our own through a problem, say, and the kind of abstractions we might discover or build when we're embedded in a community of other people. The argument that I'm making is that they're quite convergent over time. Essentially. Those abstractions that end up being really useful for solving any given problem, if you're on your own, are the kinds of abstractions that, and they end up being true and a true description of the world, they're truly useful in that sense, are also the ones that communities ought to converge to when engaged in some common enterprise. And it's accelerated by that kind of social interaction. So, happy to talk more about that later.
Great. Well, let's thank Judy Fan for that really wonderful talk. Great. And I think that Judy will be around afterwards as well if people want to talk a little bit more. So that's great. But now, let's take the stage, Jeff. Yeah. Let's take the stage, Jeff and Sean. Who's me?
Awesome? That was awesome.
Let's do another round of applause. Yeah.
I'm so glad so many of us are still here. It's great. Jesus.
Yeah, we anticipated everybody leaving
Attrition
about
off.
like 2 hours ago, so
Thank you. Can't believe this is almost over.
it is. And in fact, we're the last thing between people
Then the time
and the awards. Yeah. All right. So, wow, what a couple of days. It was
Unbelievable.
amazing. But we have, the great privilege of, kind of closing us off and really reflecting a little bit on all of the great things we saw today and the past few days. And so sadly, we didn't see any fog while we were here, but I think we had just an amazing luck with the weather as well. And in fact, we had so many more people than we thought, and hopefully you all fit in here, because in the end we had
682 registration. Can you believe that? That's awesome. I mean, it's a record. There's a nice historical plot from previous years. The color denotes some of the continents. We were in Europe and Asia, so it's interesting. But I should all be super proud about not only these numbers, but the fact that I feel like we're all kind of back, right? And that we're all enjoying each other's presence. And frankly, I think these kind of gatherings are extremely healthy and vital for our community. So I'm really glad that so many folks showed up and you felt San Francisco. I hope San Francisco was also someplace that you discovered also, and hopefully it was a draw, but also it's something that you would come back for as well. People came from all around the world for this. It was amazing.
Yeah.
So thank you again for that.
Yeah, and I think to see everyone so engaged all the way up through the end is also tremendous. And we had so many people from the local Bay Area come, as well as a lot of children that were there at the Exploratorium event. And so it was really wonderful to be here in San Francisco. So we wanted to do very fast, looking back on, what happened, and you all remember as well. But we had amazing keynotes, like at the very beginning, David Holtz, that was amazing. And then you might remember just from, how are you? Judy Fan, and I think those were amazing. But we also had, for the first time, workshops. And again, this amazing set of interactive things that were going on, wonderful discussions. I heard from so many people that it was just a really great part of that time to be able to have these long conversations that unfortunately we can't when we have, such a tight schedule. So that was really amazing. The doctoral symposium, we had the great pleasure of joining the dinner to meet the bright faces of tomorrow. This was wonderful to see, and really wonderful presentations that were given. The welcome reception upstairs at the Crown Room, we got blessed by such wonderful weather, and seeing everyone come together for the first time really made Jeff and I concerned about would we have enough food, and I guess that was a valid concern. And then the technical program, so many amazing talks. Again, I think, just to see, we said, we have, 600 people, they're gonna not fit into all of the rooms that we have for a lot of the talks, and that was also true too, because there was so much excitement, and really across both of the rooms, which we really loved to see. So many interesting questions. But not only that, we had amazing poster session and really great engagement. We saw, in the first coffee break, it was so crowded in there. But then when the posters came, the coffee line was very short because everybody was really, really engaged. And so we saw, all that great conversation. Wonderful coffee breaks, as we mentioned, and we were so lucky to have that area out there to interact in, and the beautiful views. Yeah, round of applause for the best demo session we think ever. It was so big. So we'll think more later, but really exciting to see, touch, feel, and eat, and talk to other people. Again, it was like an amazing thing. And then last night at the Exploratorium, it exceeded my expectations so much to get to see all of those demos and interactive things, as well as Jinyi Lee, who ran not only the entire banquet and planned all of it, but also was the most amazing MC for the Halloween costume contest. And so big shout out to them and all of the Halloween costume winners. Oh, there's more pictures of it as well. And
the real secret is that we actually chose San Francisco because we picked the banquet venue first. We chose that. It'd be awesome to have WIST at the Exploratorium.
It's true. And then it happened. All right, so that's basically all of what we did in the past, I don't know, 4 days in like about, 3 minutes. So hopefully you got a lot more that you'll take back as well, but it was just truly, truly phenomenal. And it's so exciting to see the level of work and level of engagement and really get to be together with so many old friends, make new friends, and see really exciting work on the human technology frontier. So, with that, we're going to pass it off to the awards session of the night. And so we have many different awards to give out. And then Jeff and I will do our closing thank yous. And then we'll pass it off to the next year's conference as well. And so we have Lasting Impact Awards, Best Demo, Juried, and also People's Choice. And we have Poster Awards and also the Best at Student Innovation Contest. So let's have Michel come up and tell us more about the Lasting Impact Award. And he's already here. Amazing.
Thank you. So this is the best job on the organizing committee, really. It's like you get to pick the most important WIST award and then to give it out. So this is, the award was created in 2003, so it's like the 21st year. And after 20 years, we innovated. This year, we had an open call for nominations, so the entire community could be involved in helping us pick the best paper. Now, we realized there was no definition for this award apart from the Lasting Impact Award, so we had to come up with one. So the WIST Lasting Impact Award recognizes the WIST papers that have had a long-lasting impact or influence on the field of user interface software and technology. The impact can be in terms of new research directions, wide acceptance in industry, or large societal impact. The or being the and or the or, of course. I was not alone to do this. On the committee, I was joined with Bjorn Hartmann, who I think was here at the conference, Toby Grossman and Jennifer Mankoff, who I think are not at the conference, but I want to thank them and give them a round of applause. So we received a number of nominations, and it was a hard decision to make because it was all very good papers, and we can only give out one award. And so the winner is a 2010 paper. Remember, the paper has to be at least 10 years old. 10 years before current year. It's a paper that has one of the highest number of citations. It's a paper that uses crowdsourcing. Crowdsourcing was big around then, right? If you remember. But it's using crowdsourcing in a way that is almost providing almost real-time answers and serving a community of people that is, I think, not paid enough attention to in WIST, and that is people with visual deficiencies. And so for those of you who have not yet guessed what the award paper is, I don't know, we have a Fairmont here connected to the internet thing, but anyway, so the winner is, I think, I know, the suspense is untenable. Thank you, Fairmont. So the winner is VizWiz, nearly real-time answers to visual questions. So so the authors are Jeffrey Bigham, who's here, Chandrika Jayant, NG G, Greg Little, Andrew Miller, Robert Miller, Robin Miller, lots of Millers, Aubrey Tatarovitz, Brandon White, Samuel White, and Tom Ye. I'm happy that Robin and Jeff are here to receive the award. The award, as you see, is this amazing piece of technology. So congratulations again. And so you have time to, give a few comments on this. And while you need to set up slides?
Yeah, if you could.
That's
No,
it.
very.
And I would say that, there's only one physical award, but all the authors will receive a certificate.
All right, well, thank you. This is such an honor.
You have to plug in.
Oh, it's on.
It's on?
Yeah. Amazing, I know. So this is such an honor, so thank you so much. So for those of you who don't know, VizWiz essentially was this iPhone app, and it allowed people who were blind to take a picture, speak a question they'd like to know about that picture, and then crowdsource answers in a few tens of seconds to any of those questions that they asked. I'm Jeff Bigham.
And I'm Robin Miller.
So what we thought we'd do very quickly, since only 2 of us of the 10 or 12 authors could be here, is talk just a little bit about the people, the time in which this took place, and then some of those impacts that were mentioned. So this is the last slide of my job talk in 2009. And I had this kind of idea, what if people could take pictures and then send them off to Mechanical Turk, which I had been playing with, which is kind of this new thing. You might recognize that the interface is actually pretty much exactly the same as 15 years ago. And Robin will tell you a little bit more about that time.
I had a great conversation with ChatGPT when we were putting this together. It told me that Justin Bieber had just become a sensational pop star at this point in time. 13 years and a lot has happened. Accessibility really wasn't a very common topic to get papers sent to at UIST at that point in time. Smartphones were still competing with feature phones. They weren't really ubiquitous. The iPhone 4 was the big announcement that year. And online marketplaces like Mechanical Turk were novel, and only nerds like Jeff were playing around with them. The gig economy was just emerging. We have come a long way since then.
All right, so as I mentioned, I just had left UW, and I spent about 6 months as a postdoc in Rob Miller's group. And this was a really amazing time to be there. People like Greg Little were building toolkits like Turkit to work better with crowdsourcing. We worked really closely with an undergraduate at the time, Aubrey, who built the first version of VizWiz for Android. Also, it was just really fun. I learned a lot from Michael. They're not authors in this paper. I just wanted to point out it was a super fun time working crowdsourcing. Michael, and then also Lydia Chilton, who's maybe here, was here. Shortly later, I went to Rochester, met Robin and some other folks.
I was an undergrad at the time and really eager to get into human-computer interaction. I actually interviewed Jeff to come to that department and worked with Hanji and Sam there to develop the iPhone app and do a lot of the user research that happened at the time.
And one of the amazing things about this paper, there's actually kind of like a second little paper embedded into the bigger paper, and it's on this system called VizWiz Located. And this came out of a visit to the University of Maryland, where Tom Ye was a postdoc, and we met Brandon White and Andrew Miller. And at the time, they had figured out for the first time how to run computer vision live on a camera feed from on an iPhone, which is a big deal back at the time, actually. And so what we did is we actually used the same infrastructure we had for VizWiz, but to send off a question for an object outline to the crowd, and then we shipped back a computer vision, a really simple computer vision model that allowed a blind person to kind of locate something in their environment. And we could do that also pretty much in real time. Shani, who is a PhD student at the University of Washington, managed a whole bunch of different things, but including the study and all of the recruitment and all of the design for this second mini paper that's in the big paper. So a lot has happened. I just want to point out a few quick things. They will be very quick. So one is, after the paper, we released VizWiz, and that was a big deal. And Erin Brady, who's now at IUPUI, she led this as a PhD student at Rochester. We collected nearly 200,000 questions and answers mostly from blind people, which gave us, for the first time ever, kind of a sense of what people even wanted to know in the visual world. You might think, oh, crowdsourcing, that's so 10, 13 years ago. But there's actually services right now that use human assistants that were aware of VizWiz at the time of their founding, like Ira and Be My Eyes, that have tens or hundreds of thousands of users. People like our own Anhong Guo was able to kind of find particular use cases that weren't really well supported by the question answering paradigm of VizWiz, and push toward things like VizLens, which used some crowdsourcing at the time. Now you can actually go find it on the App Store, completely computer vision, to support more interesting interactions, like being able to use vending machines or microwaves, et cetera. From all those 200,000 questions, many people consented to share their data to support science. We did a pretty significant scrub for private data in addition. and worked with Donna Garari to release a data set that has, for the last several years, been a challenge for the computer vision community to work on this really important, hard problem. And I'll say, when I first, in 2010 or 11, started talking to computer vision researchers about, hey, I've got this really potentially interesting new data set, none of them were interested. It was too hard, right? They looked at, anyway, open-ended question, anyway. So that has changed. So you can actually go to viswiz.org and you can participate in the VisWiz Grand Challenge, which is that computer vision challenge. We've had now the 5th annual VisWiz Grand Challenge at CVPR this summer, and we'll have the next one next year. And then there's also been products. So Yu Zhang, who's pictured here with me, he worked on VisWiz after the paper and eventually went off to Google and became the lead of Google Lookout, which is a computer vision-based system for supporting people who are blind. Microsoft Seeing AI used a lot of our data and training, and then even most recently, Be My Eyes announced Be My AI, and through a partnership with GPT-4, and a lot of the press coverage and other kind of things related that back to VisWiz. So that's quick. If you're interested, go to viswiz.org. You can learn more, and I hope you see you all various places, including at the 6th annual VisWiz workshop next year. So thank you.
Thank you.
Congratulations, congratulations. So let's welcome Thies and Michael to the stage to tell you more about the amazing demo session that we had and the demo award winners, who, when called to this stage, will come up over there for their photo.
All right, so we had like a fantastic demo program, and before we're going to kind of give the awards, I want to give one round of applause to the 77 people who have been demoing. Fantastic show, great job. Thank you so much for making that amazing show happen. So we have come to a couple of awards that we want to give out. We have 2 categories of awards. We have the Jury Awards and we have the People's Vote Award, the People's Choice Award. And so the Jury Award, we decided for 2 awards and a series of honorable mentions, goes to constraint-driven robotic services at human scale. We are going to give out the awards. You're going to come over and we'll give them all at the same time. So like kind of come to the front and then we'll give out the awards. And Z-Ring, context-aware subtle input using single-point bio-impedance sending. So one round of applause for the winners of the Jury Demo Award. And so while they're taking their picture, we move on with the honorable mentions that we have for the jury awards as well. You can pick up those awards after the closing ceremony. We have them over here. Come to the front afterwards. We'll still take a picture, but we are a little bit pressed for time, so we're going to move on right after. So the winners of the honorable mention jury awards are Mason View, Biohybrid Devices, Super Magnus Shape, Fluid Reality, and taste targeting via chemical taste modulators. Give these people a giant round of applause.
So fantastic, thank you very much, Thijs. And now we will move on to the best demos of the People's Choice. We will do the same procedure once again. So if you see this name, please come to Thijs and get ready for the photo. And the first winner is Chroma Nails, reprogramming multicolored high-resolution on-body interfaces using photochromic nail polish. And the second winner is Motohap, rendering VR performance motion flow to upper body vibrotactile haptic feedback. So, and while the groups like still making their photos, I will also read out the honorable mentions. Let's clap after I'm finished reading everything, all right? So it will be Fluid Reality, high-resolution untethered haptic gloves using osmotic pump arrays, double-sided tactile interactions for grasping in VR, and super magnet shape interactive usage of a passive pin-based shape-changing display. Huge congratulations. And again, after the session, come to us. We can then also take more photos then.
Hi everyone, I'm Parastu. I'm here today on behalf of my co-chair, Posters co-chair Doa, who couldn't be here today. Thanks to our Posters committee members, the 10 committee members who helped us select 50 posters. Thanks to all the poster presenters. I hope you enjoyed seeing those. I'm going to introduce the Best Poster Award, and it goes to Virtual Body Redefining Conversational AI Interactions for Individuals with Hand Motor Disabilities by Atiya Tahiri and colleagues. If you can come to the front and take a photo with Sean and Gabriel. We also have 3 honorable mention awards. Again, please come after the event to collect yours. You no need to come up, but I'm just going to read the titles. Sketching related work, finding and organizing papers through inking and node link diagrams, an interactive system for drawing cards in perspective, generative facial expressions and eye gaze behavior from prompts for multi-human robot interaction. Now I'm going to pass it on to Jason and Brian for the Student Innovation Contest.
Hello. So for this year's SICHI, we have 10 amazing student teams working on large language model-based interactive systems. And so please give all the students a round of applause. And we have 3 amazing juries, Takeo Garashi, An Hongguo, and Amanda Spurgeon, who joined our SIC and really gave great feedback to the teams. Now I'm going to announce the jury award for the SIC. The jury best SIC goes to Lingoland, an AI-assisted immersive game for language learning from Olivia Su from Harvard University. Please come to the front, Olivia. Okay. I'll keep it now, yeah. Okay, so again, for the honorable mention, we will give out the award after the ceremony. So the honorable mentions go to Autolens, configurable LLM-generated audiences for public speech practice, from Junggung Park, and Da-Yoon Choi from KAIST. And the other honorable mention goes to Docent, Digital Operations-Centric Elicitation of Novice-Friendly Tutorials from Yihao Zhu and Qingyi Zhou from Tsinghua University.
Okay, yeah. So we also had a People's Choice Award, a couple of People's Choice Awards, and these were again chosen by votes. The People's Choice Award goes to Smart Pikachu, extending interactivity of stuffed animals with large language models by Toma Itagaki and Richard Lee. Okay. And there were also 2 People's Choice honorable mentions. So there was a 4-frame manga drawing support system by Yuto Nagao Soichiro Fukada. And finally, there was Xenify, transforming research papers into engaging zines with large language models by Jaidev Sriram and SPK Srikala.
All right, well, let's thank all of our award winners across all of the sessions. Well, that means that this is basically the end of UIST 2023. But as I think we all know, there's so many people that made UIST possible, and we wanted to take a little bit of time to thank the organizing committee. On Monday, we thanked also the program committee as well as the ACs and external reviewers, but let's thank all of those people once again for all their contributions. All right, so first off, we want to thank our amazing sponsors who really made this, this whole event possible. So of course, the funding groups that we have, our organizations, ACM, SIGCHI, and SIGGRAPH, they really gave us a lot of support along the way as well. And then our platinum level sponsor, Meta Reality Labs. Yeah, here, what are you doing?
Oh, yeah, I keep saying Facebook Reality. It's Meta. Let's give them a big round of applause. And to our silver sponsors, Adobe, Apple, Autodesk, and Google. And our bronze sponsors, TRI, JP Morgan Chase, and Cicero. And for the student innovation sponsor, Anthropic, thank you.
So, but especially we want to thank the 2023 organizing team. As we said, this has been, a long time coming, but we really wanted to highlight a few people that have been doing so much at the very beginning, and that's the student volunteer chairs, Mina Hu and Tisha Setkepak. I don't know if they're here, but they are really the people that make this work, and we are so privileged to get to work with them. And it was such a seamless experience for both Jeff and I because of that. And so obviously, in addition to Tisha and Mina, we have 34 amazing SVs that all contributed and made everything work so much. And so this is just a few of them, but here are all of their names. And again, let's thank all of them for all the hard work that they did. They, again, are just, this is an amazing group of people and students, and I hope that you got a chance to talk more with them and get to know them. It was truly exceptional. So we'd like to thank the program chairs, Jürgen Steimle and Natalie Risch as well. Then our program subcommittee chairs, Pedro Lopez and Rio Suzuki. Our amazing money people, the treasurers that made all this possible, Dan Afrigan and Sang-Wan Lee. We thanked Jeannie earlier, but I think they deserve all the thanks in the world for making the banquet and all of this possible. So Jeannie Lee for local arrangements. Woo! Woo! Go Jeannie! Also, Jeannie gets the Best Organizer Costume Contest Award, so they win there. All right, the demo chairs who we just heard from, Tice and Michael. And then our wonderful poster chairs, Dohan, and Parastu Abtahi, who we just heard from as well. Then we had an amazing team of doctoral symposium chairs who gave all of these students amazing guidance. Let's hold our applause till I read out all the names. Alex Ion, Mary Morris, Michelle Boudon-Lafon, Anand Gowa, and Takeo Igarashi. So, round of applause to them. All right, our amazing Visions chair, I think Visions was an amazing track this year, as it always is, Alex Owal. And for the first time, we had workshops, which meant that this was an extra especially hard job because there's no institutional knowledge here. So let's give a huge, big round of applause to David Lindelbauer and Elena Glassman for a huge success. I hope we bring workshops back.
We have to.
Yeah, we have to. All right, Michel again, you see his name multiple places because he's been so great. Michel Boudon-Lafon for the Lasting Impact Chair. Our amazing awards chair who sadly couldn't be here, Andy Wilson. You know him, you love him. Our amazing student innovation chairs who really pulled an amazing together program with basically actually zero budget that we gave them. So, so we were like, do it for nothing. Brian Wang and Jason Wu, who, yeah, woo, that was a great set of SIC awards. All right, there's more. So the web chairs who made the website possible, Jeremy Warner, Vivian Liu, woo. Our amazing publicity chair, Anusha Withna. Our two great sponsorship chairs, Valkyrie Savage and Stephen Oni, who again made this possible thanks to the sponsors. The preceding chairs, Zian Yu and Liang He as well. Our amazing registration chairs, Lawrence Kim and Cheng Zhang. And I want a huge shout out to Yihao Peng, who did such an amazing job with accessibility at this event. I think it was really quite phenomenal. Celine, of course, who represents SIGCHI Cares for us. And big shout out to Alexa Su, who brought back the women's luncheon and many other things in the diversity chair role, and we really appreciate their help and support. Thank you, Alexa. We heard so many great things about that event. And then our data chair, Tian Wu, thank you so much. And video previews and video chair as well, Faraz Faraki, let's hold our applause to the end, Faraz Faraki, Stephen Villa, Seilan Yang, Juni Zhao. Okay. Zulu. Whew. That's everybody. We thanked them all. So let's thank everybody again.
Stand up. Anyone here, stand up, please.
If you contributed, even if we didn't call your name, stand up and
Please.
okay, or stay seated. Yeah, okay, for us, okay, well, let's move on. All right, but most of all, thank you all for coming and making WIST 2023 possible and amazing. I think this far exceeded anything I imagined in terms of how great it was going to be.
No, it was amazing, and I also hope you realize why both of us call the Bay Area and San Francisco our home, and I hope you fell in love with it a little bit. So thank you all for coming.
Yeah, and thank you, Jeff, for doing this as well.
Thank you, Sean.
Oh, yeah. We forgot to put ourselves in that. We did it. It worked out. Okay. All right. So that means that Jeff and I are done. So we're going to go on a long-needed vacation. But that means, you know, after every WIST, there is a Chi. But then again, there is a WIST. And so onwards and upwards to 2024, and we are delighted to announce the organizers for WIST 2024. Don't go to Chi, no, just go. Anyway, the WIST 2024, that is Lining Yao and Mayank Goal. So, they're going to tell you a lot more about the amazing program that they have planned for you in 2024 in just a moment, because I couldn't download the slides.
I will say one last thing.
Yeah, let's say one more thing.
Throughout this entire process, I've gained so much respect for every previous general chair that's ever done this. So really, it's amazing. So
let's thank all the previous general chairs. Yeah. If you did this,
it's amazing.
All right. All right. And let's thank one who's about to know what that really means.
Yeah, exactly.
Good evening, everyone. So we'll have WIST next year again. We are not done, right? So WIST 2024, I'm one of the general chairs, but Lining Yao, she couldn't come here due to some health reasons. Both of us are at CMU. She's transitioning to Berkeley, but right now, still at CMU. It'll be in Pittsburgh because it's easiest for us to organize it there. It's an amazing city. All sunrises are exactly like this in Pittsburgh, so we are sure you'll have a lot of fun. The conference is going to be from October 13th to 16th, so no Halloween party. So don't bring your costumes. We'll have some other themes, but no Halloween party. You can enjoy Halloween with your families. So we were thinking of what the theme should be for WIST next year, and we thought of bridges, because Pittsburgh is really a city of bridges. But they stole the bridge theme this year. There was a bridge. Our bridges we have more bridges. They are more beautiful. Arguably, Pittsburgh has most number of bridges in the whole world, like it's a city with the most number of bridges, but that would by definition be incremental, one bridge to many bridge, and not novel enough for WIST. So we gave up on that theme for now. We don't know what the theme would be, but it'll be fun, it'll be funky, and we really look forward to welcoming all of you to WIST next year, and I'm sure you'll have a lot of fun. So we are still looking for organizers. We have some roles that we have finalized. The program chairs are going to be Alexandra Ion from CMU and Pedro Lopez from University of Chicago. I almost said Washington. And then we have finalized our local arrangements chair as well. That this was a no-brainer for me. I don't know anyone else who's a bigger champion for Pittsburgh, who's a part of the WIST community. So I cannot imagine organizing WIST without Chris. He has already been a huge help. So thank you, Chris, already. And we need your help to organize the conference. You just heard how hard it is to organize the conference. So we actually last month released an application on Twitter and maybe some other social network as well. So I've added the QR code for that here as well. If you want to be part of the organization team, please use that link to add your application. We already have, many of you have already applied. We have like 150 applications. I'm not looking forward to going through those applications, but just to add more work for myself, please, if you are interested in helping us and haven't already done it, please do that. And yeah, we look forward to seeing you next year.
So it's over. Thank you all. Enjoy the city of San Francisco. Go out, do amazing things, and we'll see you next year in Pittsburgh.